Aloha class, chapter 9. This is it, BC, but it is long, all right? And so we need kind of an introduction. We don't do much of it, unfortunately, throughout our curriculum here at Manuka High School. So we're going to kind of do a brief introduction here of what sequences and series are, okay? So here we go. A sequence is simply a list generated by a rule. And our rule is denoted by the term A sub n, okay? And a sequence is just a list. So if you look right there, A1, comma, A2, comma, A3, okay? Those are all terms of a particular sequence. And once again, the rule for a sequence is usually noted by A sub n, okay? Here we go. Let's just get after it. Example 1. All right, so example 1, let's roll, give me them toes. All right, sequence 2, 4, 6, 8 is a sequence of even numbers. All right, and so if we look at this, 2, that'd be like A sub 1. 4, that'd be A sub 2, right? And then we have 6, A sub 3, 8, dot, 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 comma. What would the rule be for that, right? It would be A sub n, but we make up a rule for that. If you think carefully, maybe it's 2n, right? That would be of the even numbers. Plug a 1 in there, right? A sub 1, 2 times 1 is 2. And thus, that would be a sequence, okay? And the rule would be A sub n is equal to, and we usually write it in little cool little braces there, 2n, okay? And that's a way that we write a particular sequence, which again, is a list of numbers. Okay, let's look at the odds. Okay, let's say that's question 1, question 2. And the odds would be 1, comma, 3, comma, 5, comma, dot, dot, dot. What would the rule be for that one? Well, if you notice, we jump by 2 each time, right? So that, again, is of the same idea of a 2n. But if you notice, we start at 1 this time. So what could I do to do that? Well, I just maybe have to subtract 1. And there would be our rule for that particular sequence. Now, don't get so stressed out. We don't have to really come up with these that much on the BC exam, but we should be aware of what they come from, okay? So those are ideas of what sequences are, okay? Note, when given a sequence as a list, the first term is usually designated to be associated with n equals 1. This is because we are using n as a counting number rather than a cardinal number, okay? It just means we're counting. Example 2, okay, this time they actually give us the sequence, okay? And the sequence, the rule is 4n over 3 plus 2n. And they asked me to list out the first 5 terms. Well, how would I do that? Well, A sub 1, right, would be plugging a 1 in there, so that'd be 4 over 5. Everyone with me? Right, A sub 2 would be plugging a 2 in there, which would be 8 over 7, right? A sub 3 would be plugging a 3 in there, which would be 12 over 9. And I've got these down here on my paper, you guys. A sub 4, 16 over 11. If you look at the bottom there, we're jumping up by 2s. Once again, it's by that term right there. On the top, we're jumping up by what? We're jumping up by 4s, right? So once you get it going, you can go quicker and quicker. Okay, now they asked me to list the first 5. There you go. There's my list of the first 5 terms of that particular sequence. But they also want me to examine or investigate what happens as the limit as n approaches infinity, right? We've done this stuff already this year. Well, doing this particular limit, right, class? That's an n behavior model, right? Or that's a infinity over infinity. I could L-hop that bad boy and use L'Hopital's rule, right? Or we could use n behavior rule. A lot of different ways to do it. This would be 4 over 2, which would be equal to 2. Huh. Quite interesting. Do you know what that means? That means if I continue to list these guys out, it's going to approach the number 2. And it kind of looks like that, right? It starts at 4/5, 8/7, gets to 20 over 13. If I list an infinite amount of these out, guess what? I am going to get to the number ni, right? 2 in Japanese. All right, let's keep on rolling. And that's how we're going to inspect some of these guys. And, you know, it said it earlier, one of the important things here in this chapter 9 is when we deal with sequences or series, which we're going to find out in a little bit, are we converging or diverging, right? And this looks like this particular sequence would actually converge to the number dos, okay? And that's something we want to be aware about. Factoid. All right, here we go. Here's a very important fact for us here in BC when we're talking about sequences, okay? So let's say we have a sequence. If your limit goes to infinity, then we say the sequence diverges to infinity. If the limit of that rule goes to negative infinity, then we say the sequence diverges to negative infinity. But let's say 3, the limit approaches a C, a finite real number. Then we say that the sequence converges to C, just like the one we did up above, right? And then 4, what if the limit oscillates between 2 fixed numbers? Then we say that sequence diverges by oscillation, okay? Here we go. Now, one thing that I found very interesting as I teach BC every year is how many students have not been introduced to this factorial bad boy, right? It's in our calculator. We need to be familiar with that guy. What is n factorial? N factorial, here's a good example. Por ejemplo, I don't know. All right, here we go. Por ejemplo, 9 factorial is just 9 times 8 times 7 times 6 times 5 times 4 times 8. So obviously a very, very big number. 5 factorial, right? What's 5 factorial? 5 factorial would be 5 times 4 times 3 times 2 times 1. And here's a very important knowledgeable thing we should know. What the heck is 0 factorial? Well, believe it or not, 0 factorial is equal to 1 factorial. How can you say so? Well, because by the rule, 1 factorial would be equal to 1 times 1 minus 1 factorial, which would be 1 times 0 factorial. And the only way this stuff could all be true is if 0 factorial was equal to 1 factorial. Therefore, 1 factorial, ichi. 0 factorial, ichi. Okay? You need to know that. All right, here we go. Let's go ahead and use these factoids with the ideas of limits to help us out here a little bit, okay? Once again, I cannot get this thing skinny. Okay, it writes fat. I apologize that. We're just going to have to erase some, take some good notes. All right, determine whether the following sequences converge or diverge. Now, how can I do that? Well, I can just take a look at the limit. Okay, so let's do the limit. N over n plus 1. Well, that's infinity over infinity. You could L-hop that bad boy, or just use our rational function, right? And behavior model, that would be ichi. So then we would say that converges to 1. That sequence will converge to 1. All right, let's go ahead and do this next bad boy, the limit as n approaches infinity of 1 over 2 to the n. Well, we all know that guy is going to be 0, right? So guess what? That dude converges, but that one does not converge to ichi. It converges to 0. Make sure you take the good notes, right? I got this big pen. I can't write all that stuff down there, okay? Here's the next one. What about the limit as n approaches 0 of 3 plus negative 1 to the n? Ooh, this one's kind of interesting. Shoot, how do I... There's kind of like an alternator there, right? It's going to like be 3 plus a negative 1, and then it's going to be 3 plus a positive 1, right? Because if it's even, it's going to turn that negative to a positive. So what I want to do in a situation like this is maybe let's list some of these guys out, okay? Let's list some of that sequence out. Okay, so let's start at 1. If I start at 1, it would be 2, right? Let's put a 2 in there now. What's a sub 2? A sub 2 would be 3 plus 1, which is 4. And guess what? Oh, snap. That looks like it oscillates between 2 fixed numbers. So what do we say? It diverges by oscillation, right? Okay. Let's keep rolling. So sometimes you can't do a limit. Something seems a little So maybe list a couple of those guys, and it can give you an idea of what's going on. All right, this next bad boy, the limit as n approaches infinity of n over 1 minus 2 to the n. Well, don't try to trick me by putting that in second. You can't get that past me, right? That's just an n behavior model, or L-hop, right? But I don't need to use L-hop, so I'm just negative 1/2. So it converges to negative 1/2. Did I get it right? Booyah! I'm like 4 for 4. All right, let's do this next bad boy. I'm going to erase some of these guys so we don't get a little bit confused as we go problem to problem. Let's do the limit as n approaches infinity of the natural log of n over n. Oh, snap. That's infinity over infinity. We got to L-hop, right? So what's L-hop? Well, that means technically, right, we learned this earlier. To use L'Hopital's rule correctly, I've got to write it as 2 separate limits, right, class? Okay, And I get that. And then what I do is I take the derivative of the top. The derivative of the top would be 1 over n. And you're only allowed to do this, remember, if you get the indeterminate result of 0 over 0 or infinity over infinity. On the bottom, I just get ichi. Okay, now if I take those limits, I get 0 over 1. Oh, that's 0. And since it's 0, that means it converges to 0. All right, let's keep on rolling. Okay. Boom. Pen. Limit. Ooh, sweetness. We got this little factorial bad boy. So we have n factorial over n plus 2 factorial. How the heck do I do this bad boy? Whew. Well, you got to know that rule of factorials. Remember, if it was 9 factorial, it would be 9, 8, 7. We're always subtracting 1, right? So believe it or not, I could rewrite that denominator, okay, because it's always going to go down 1. And I want to rewrite it until maybe I get something I can cross out, right? And then it gives me a little bit more information of what's going on. But this is equal to infinity over infinity. It's not like we can use LHOP. We can't find the derivative of a factorial. On the top, I'm just going to keep that as n factorial. But on the denominator, I can write that as n plus 2. Let's subtract 1 times n plus 1. Let's subtract 1. Well, and then I just keep on going. And look, at some point, we're going to be repeating. Okay, so those guys could cancel out, which gives me a limit as n approaches infinity of 1 over n plus 2 times n plus 1. Well, that's easily 1 over something enormous, which would be 0, converges to 0. How about it? Let's keep going, class. Ooh, we only have 3 more. These aren't too bad, huh? But remember, this is not really much of BC. This just gives us an introduction of what sequences are and this idea of converges versus diverges. Now, it's very important. Remember, all of these problems here are sequences. It's just a list of numbers. So if I were to continue to list these bad boys out, would they just go to infinity, get bigger and bigger and bigger and bigger? Go to negative infinity, get smaller, 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 smaller? Or would they actually converge to a fixed number? And any one that we get converges, it actually does. All right, let's look at this next guy. Okay, if you notice, we're always going to get something that there's maybe something a little different we got to think about. And that happens with this one, right? We can't do, this is infinity over infinity. And we can't take the derivative of a factorial. So here you just have to be, you need to know your functions. That's an exponential up there. So it's going to grow pretty fast, but a factorial grows this crazy style, okay? So the bottom grows so much faster that this is actually going to converge to 0. Okay, this dude we skipped in L'Hopital's rule. It's like a log L'Hopital rule. It's actually pretty cool how we work that out, but it's not a BC thing anymore, so we're going to keep rolling. This last one, same thing. You just better know about these functions. So I'm telling you about them now, and you got to know them from here on out, okay? This dude, stupid. No dude grows faster. Like, that's a big bad boy. Okay, that's the big bad boy on the lot. Nothing grows faster than that bad boy. So even though the top is a factorial that grows really, really fast, that's going to be something over something that's even way bigger. So that converges to 0 also. Okay, make sure you remember those things. Sometimes they can be very beneficial on the AP test if we have like multiple choice questions. Okay, that's how we use a lot of that information of some of those like functions of which grow faster than the other. Okay, let's keep going. All right, example 4. Ooh, these ones here. Now, once again, I said you don't really have to do this much on the AP, but we kind of don't do this much in our curriculum. So we're going to talk about this, all right? We have 3, 8, 13, 18. Now, one very helpful thing to do whenever you're given a sequence to determine if you can come up with the nth term or the rule is you always take the second guy and you first try subtracting it by the first guy, and I got 5. Okay, and then you take the third, subtract it by the second. And if you get something common using a subtraction, then that means this is an arithmetic sequence. And anytime you have an arithmetic sequence, should be kind of okay to write the rule. And the rule for this one, believe it or not, is since 5 is that common difference, it's going to be 5n. Okay, and then you just have to make sure we start in the right place, right? We're not starting at 5 because 5 times 1 is 5. Instead, we're starting at 3. So if I was to put a 1 in there, I get 5. Just take away 2. And guess what? That is your rule of that sequence. Okay, and you should test it. Let's put a sub 2. Let's put a 2 in there. And a 2 in there would be 10 minus 2, which is 8. So it checks out beautifully. So that's a good test to always do, okay? And if you get a common difference, right, if this number is the same each time I subtract, then that means it's an arithmetic sequence, okay? Arithmetic sequences are something we want to be aware of, all right? All right, here we go. Let's go to the next one. Let's check if B is arithmetic. I'll kind of do my notes over here. We got negative 15 minus 5. I got negative 20. Okay, and then let's go 45 minus negative 15. Oh, snap, I got 60. Okay, there's no way it could be arithmetic. Well, here's another one. Okay, if we subtract them, guess what else we could do? We could divide them. Okay, let's divide these guys. Let's do negative 15 divided by 5, negative 3. Let's do 45 divided by negative 15, negative 3. Let's do negative 135 divided by 45. Oh, negative 3. Oh, snap. Now, if I have a common ratio, we say, and the ratio here is you're kind of multiplying every one by a negative 3, right? So we have a common ratio from term to term. That's called a geometric series. And whenever you have a geometric series, okay, we write down where we're starting first. Where are we starting? We're starting at 5. Okay, we put whatever our common ratio is smack dab right there in parentheses. Okay, my common ratio is negative 3. And then I just have to put an exponent on that guy. Now, if I put an n on there, that would be inaccurate because if I put a 1 in that bad boy, it'd be negative 3 to the first, which would be negative 3. 5 times negative 3 is negative 15. But guess what? I can just do that, and then it works out beautifully. How so, Mr. Tight? Well, if I put a 1 in there, negative 3 to the 0 is 0, and I have 5 times 1, right? Because negative 3 to the 0 is 1, I'm sorry. 5 times 1 is 5, and that's my first term. Let's check the second term. Second term means I put a 2 in there for n. 2 minus 1 is 2. Oh, that's 15. Let's try another one. Treat. Put a 3 in there. It means, oh, I'm going to square it, and I get 9. 9 times 5 is 45. That dude works out. Now, these first two, A and B, are the most important, okay? We have arithmetic and we have geometric sequences. You should be able to write the rules for those. Okay, and then these next ones are just some fun ones to kind of look at. Go ahead and see if you can just come up with what you think these rules would be. Okay, in terms of what's important for us, I'm just going to keep rolling because I know we don't want to keep this video crazy long. All right, make sure I go over those next class, and we'll give some bonus points out, maybe give you a chance to win some candy, all right? But here we go. Let's get really to the nuts and bolts of what this first section is all about. And it's not about just listing numbers and getting sequences, right? Homes, right? It's all about a series. Now, what's the difference between a sequence and a series? Well, a series is a sum of the sequence. Okay. And we have what we call infinite series, and we have what we call partial sums. So an infinite series is if you added these dudes up as they go for infinity. And just like earlier, if I was to add something up, just add up every single number in the world, would it diverge? Would it converge? Some people would think, hey, it always have to diverge. No, not true. Okay, and we're also going to look at partial sums. Okay, we use partial sums sometimes. When we want to get a range, you know, what would it maybe if the series converged, what would it converge to? We can't always figure that out. Okay, we can't because it goes on forever. Okay, this guy we're probably a little bit familiar with. A sum is sigma, right? It's a capital letter for S in Greek times. All right, that means we're going to just sum everything up. Okay, and in sequence, we usually give us a sequence, right, which would be a rule, a list of numbers. And then if we put this little dude out in front, that means you are going to sum those bad boys up. When we use that sigma dude, okay, that means you got to add up everything in that sequence. And then guess what? We're going to ask you if that converges or if it diverges. Sweetage. All right, I think I'm back at it, all right? So let's go ahead and look at some infinite series, okay? We're going to look at these two sequences right here, but we're going to sum these bad boys up, right? So if I just take that, and we're going to use our calculator here to first examine these guys, okay? So let's sum up from n equals 1 to infinity, 1 over n, and let's go ahead and sum up n equals 1 to infinity of 1 over n squared. And what do you think happens with those guys? Do you think they converge or if they diverge? Now let's take an idea. Let's just start listing some of these out, okay? So let's put a 1 in there. 1 over 1 is 1. Okay, plus, why plus? Because we've got the sigma dude, right? I'm going to put a 2 in there. That's 1/2. Plus 1 over 3. Oh, snap. Plus 1 over 4. Oh, snap. Plus 1 over 5. Oh, snap. Plus dot, dot, dot. Now, the question is, if I sum these dudes up, like S sub 1 means you're summing up one of them. That's called a partial sum. S sub 2 means you're going to sum up the first two guys, 1 plus 1/2, and I got 3/2. Boom. S sub 3 means you're going to sub 1 plus 1/2 plus 1/3. I get an answer of 11/6. Okay, what's our thought? What's your thought right now? Right? Ooh, I almost tripped. What's your thought right now? Do you think those sums will add up eventually to a particular fixed number? Or do you think those dudes are just going to get bigger and bigger and bigger? Take a guess. Let's look at this next one, right? Plug a 1 in there. I get 1. This is just listing them out. Plus, plug a 2 in there, 1/4. Plus, plug a 3 in there, 1/9. Plus, plug a 4 in there, 1/16. Oh, snap. Put a 5 in there, 1 over 25. Plus, dot, dot, dot. And I could do the same thing with partial sums. I'm actually going to do our calculator. I'm going to show you how I look at this. But you've got to right now make a determination. One of those series means I'm adding up all of those numbers, converges, and one of them diverges. Take a guess right now, and then get out your calculator. Okay, because we're going to look at this and how we can use our calculator. I found this cool new button in my calculators that I could hit alpha window. And it's a shortcut for some of these hard things that you have to find in your calculator. Right? And you can go between these things, matrix. You can go right to polars because I'm in polar mode. And there we go. And guess what? I'm going to sum these bad boys up. Right? So I'm going to use the little sigma guy. Now, believe it or not, it doesn't matter what variable you use. However, we are in sequential mode. So let's all go to mode. And how about it? You guys are so well advanced now in BC that we've done function mode in BC. We've done parametric mode. We've done polar mode, and now let's go sequential mode. Okay, second quit. Let's get back. Let's go ahead and examine what happens here and give ourselves an idea of what's going on. Okay, so let's go. Can I go down? Ooh, it looks like I can't go down, maybe because I changed mode. So alpha window. Ooh, maybe I should use my little guy right here. Maybe it will work a little bit better. We'll go down 1. Boom. Okay, we're going to go n, right, from 1. Let's just examine here. Let's go 1 to 100. And we're doing this for 1 over n. Let's see what we sum up to. 50. Okay, so, 1 over 2. What are you doing? What are you doing? Second, enter. Let's get that bad boy back. I want 1 over n. I knew something was n. Boom. Enter. 5.18. Okay, let's go a little bit. Let's examine. Let's go second. Boom. What happens if I go all the way to 1,000? Right, and this can give me an idea. Do you think we are converging to a specific number? This will probably give me an idea. It's probably going to think for quite a bit here, so let's just jam out. Oh, okay, 7.48. Can you see that? Oh, you can't see that on that side of my calculator. Okay, so my best guess, that dude diverges. Okay, and believe it or not, it does. Remember, that's called a harmonic series. We did some of that when we did P series, if you remember. Okay, 1 over n to the first. All right, now let's go ahead and look at what happens if, let's go ahead and get used to this alpha window guy. Man, this dude's helpful, right? Absolute values on there. You got your derivative, your integrals in there. You got your log base. You got your x root. Okay, so this is a very helpful button. You're welcome. Okay, but this time let's go n equals 1 because we're going to go from 1. Okay, let's go to just 10. Okay, but this time let's do that second one, which is 1 over n squared. And if you notice, this is kind of related to P series 2 as we did before. Let's see what we get there. But 1.549. Interesting. Let's get a little bigger here. Right, let's go to 100. Okay, 0, 0. Let's see what happens. Okay, let's do it. It's good. Probably good. It looks like we're converging to something there, doesn't it, class? Let's do one more just to really check out what's going on. But I don't know about you. I think if I had to make a guess right now, I would say this converges. Okay, and if it converges, believe it or not, I can't find out exactly what it converges to. But just by examining this, I've got, 1.643 for sure, right? Because this is as we go to infinity. It definitely looks like it's maybe going to 1.6, 1.65, right? Would maybe be my guess of what it converges to. But there's no way of really telling for this particular equation. Okay, for some there are, and that's what we're going to discover here as we go on MBC, all right? All right, there you go. Hopefully you had a good guess. Hopefully you guessed those right. How many people did? Raise your hand. Okay, but here we go. We're just gonna keep rolling talking about this stuff. I think I got a couple more examples. We're gonna cut this video a little short, and then we're gonna get into some of these crazy tests that we're gonna have to do. Okay, but let's go ahead and introduce this convergence and divergence of a series, and we're gonna look at our very famous geometric series. Okay, but if you look right here, here's a list. A list. If you were to add up all of that stuff, right? And why is it called a series? Because it's got that sigma guy, right? If not, it'd just have that rule, and it would just be a list of numbers with commas in between them. But I don't know about you, but look at these guys. That definitely looks like it is going to converge. Okay, and believe it or not, it does converge. Okay, and let's think about some things. Once again, we could do a partial sum. You could add up the first one, then add up the first two, add up the first three. And as you add them up, it gives you a good idea of what is going on. Okay, but that is an idea of a geometric series. Now, why is it a geometric series? Remember, I had said you had to write this. You had to write down your first term and then your common ratio. Okay, and there is my common ratio. That's one way you could write it. Okay, another way I could have write it is my first term actually is 3/2. Okay, that's my first term is actually 3/2. And what is my common ratio? I just keep on multiplying by 1/2. So there's actually two ways you could write this rule. And instead of an n, because that wouldn't be true, my first term, if that was the case, would be 3/4. I'm an n minus 1. Both of those are actually ways that you write a geometric series. Okay, interesting, right? And some of you might be, well, maybe I could go a little bit further. And you could, but let's not get cray, all right? But this is an example of a series that converges. And it's a very special series for us. It's a geometric series. Okay, now let's go down and look at this bad boy. Once again, still a geometric series. Well, how do I know it's a geometric series? Well, there's a common ratio. I keep on multiplying it by 3/2. Well, what is your first term? Guess what? It's 3/2. What do I multiply it by? It's 3/2. Okay, but then it would have to be an n minus 1, remember. Okay? And there we go. That is our rule. If you look up there, it's obvious those numbers just get bigger and bigger. Well, that dude's definitely going to diverge. Now, this one here says to list out the first 5 terms of your partial sums. So I'm going to do that for you just so you have an idea of what it is. Did I already write it down? I didn't. So I'm not going to do it. Okay? Because you easily, that's your job right now. Put these in your calculator. S sub 2, S sub 3, S sub 4, and S sub 5. And you're going to notice they just get bigger and bigger and bigger. So, hey, you can make the idea that it diverges. Now, believe it or not, if I was to go up a little bit, we have these really cool tests. Sweet. And why are those so sweet? Because that means we don't have to put these in our calculator. We don't have to observe what's happening. We just have to pay attention to some very important rules. And then we can use these tests to help us to determine whether certain series diverge or converge. And sometimes when these series converge, we can actually find out what they converge to. Sweetie, sweet. Aloha. Whoops.